The Cafferty Group, technical service advisors with offices located in Nebraska, Iowa, Kansas, and Colorado, presents Essential HVAC Principles, HVAC System Diagnostic Fundamentals. System Troubleshooting Techniques. Where do I start? Don't let it intimidate you. Is it a system problem or a unit problem? Gather all the facts. If not factory installed, then connect all measuring instrumentation as needed. Manifold gauges, suction line temperature sensors, liquid line temperature sensors, duct pressures. This presentation will discuss troubleshooting and evaluating refrigeration systems that use capillary tube and expansion valve metering devices. Other presentations cover airside and electrical system troubleshooting. Indicators. Proper measurement and interpretation is the only way to determine proper operation and performance of an HVAC system. The service technician must develop these skills and use them correctly. Items to be measured and evaluated include head pressure, suction pressure, superheat, subcooling, amperage, evaporator air delta T or temperature difference, condenser air delta T, and observation. The arrow chart. Let's talk about troubleshooting methods. The method we will use is commonly referred to as an arrow chart. For each of the problems that we look at, we will discuss how the system should look on your test devices. First, we'll discuss capillary systems such as cap tubes and metering pistons. Then we'll talk about expansion valve systems. Problem possibilities for capillary tube metering: overcharge, undercharge, refrigerant system restriction such as a dryer, low evaporator airflow, dirty condenser, low outside ambient air temperature, and inefficient compressor. Problem possibilities with TEV or thermostatic expansion valve metering, also referred to as a TXV. Overcharge, undercharge, refrigerant system restriction, low evaporator airflow, dirty condenser, low outside ambient air temperature, inefficient compressor, sensing bulb lost its charge, loose sensing bulb, improperly insulated sensing bulb. Let's take a look at expansion valve issues and their cause and effect. In an overcharge situation, the head pressure would be high. Suction pressure would be normal to high. Superheat, normal to high. High subcooling, high amp draw, and normal to low or high delta T across the evaporator. In an undercharge scenario, low head pressure, normal to low suction pressure, normal to high superheat, low subcooling, low compressor amp draw, and normal to low evaporator delta T. With a refrigerant system restriction, head pressure could be low or high, depending on the location of the restriction. Low suction pressure, high superheat, high subcooling, high or low amp draw, and a low evaporator delta T. In the case of low evaporator airflow, low head pressure, normal to low suction pressure, normal to low superheat, high subcooling, low amp draw, and a high evaporator delta T. A dirty condenser may cause high head pressure, normal to high suction pressure, normal to high or low superheat, low subcooling, high amp draw, and a normal to low evaporator delta T. Low outside ambient temperature can cause low head pressure, normal to low suction pressure, normal to high superheat, high subcooling, low amp draw, and a low evaporator delta T. Symptoms of an inefficient compressor could be low head pressure, high suction pressure, high superheat, low subcooling, low amp draw, and low evaporator delta T. A TXV bulb that has lost its charge, you could experience low head pressure, low suction pressure, high superheat, high subcooling, low amp draw, and a low evaporator delta T. A TXV bulb that has come loose from the suction line may cause normal to high head pressure, normal to high suction pressure, low superheat, low subcooling, high amp draw, and high evaporator delta T. A TXV bulb that is connected but not insulated could cause normal to high head pressure, normal to high suction pressure, low superheat, low subcooling, high amp draw, and high evaporator delta T. High superheat. High superheat is an indication that the evaporator is starved for refrigerant for the heat load that is present. Some possible causes of high superheat may be low refrigerant charge, liquid line restriction, evaporator airflow too high or an excessive load, metering device not feeding correctly, incorrect metering device, low outdoor ambient temperature, liquid line exposed to high ambient temperatures, excessive liquid line pressure drop. High superheat from a low refrigerant charge. If there is not enough refrigerant in the system, the evaporator will be starved. The refrigerant will be totally evaporated earlier within the coil. As a result, the vapor will stay in the evaporator coil longer, so it will pick up too much sensible heat. The excess heat picked up by the vapor causes a higher than normal superheat. If the system has a low charge, both suction and discharge pressures will be lower than normal. Subcooling will be lower than normal. High superheat caused by a liquid line restriction. A restriction in the liquid line will prevent adequate liquid refrigerant from being fed to the evaporator. This will cause many of the same symptoms as a low refrigerant charge, with the primary difference being the amount of subcooling. Quite often, you'll see a noticeable temperature drop at the point of the restriction. A partial liquid line restriction will decrease the suction and discharge pressures, or may increase the discharge pressure until a safety trips, depending on the restriction location. A complete restriction or blockage will cause both pressures to be much lower than normal. High superheat from excessive evaporator airflow. Excessive airflow across the evaporator coil increases the heat load, reduces the moisture removal capability or latent capacity of the equipment, reduces the evaporator delta T. The refrigerant vapor picks up an additional sensible heat, which in turn causes a higher than normal suction pressure and a higher than normal superheat. High superheat as a result of excessive load. Excessive load conditions overload the evaporator, increasing its superheat. When checking superheat, consider the conditions that the system is operating in. If warmer than design conditions, the system may not meet the demand. Low superheat. Low superheat indicates that there is an excess of liquid refrigerant in the evaporator coil for the heat load that is present. In this case, it is likely that liquid refrigerant is present in the suction line and may possibly enter the compressor, causing compressor failure. Some possible causes of low superheat could be refrigerant overcharge. The metering device is overfeeding. Low evaporator airflow. Oversized equipment. Low condenser airflow or a dirty condenser. Low indoor heat load. Low superheat due to a refrigerant overcharge. An overcharge of refrigerant can force excess liquid refrigerant into the evaporator due to the high pressure differential across the metering device. The excess refrigerant does not absorb enough heat in the evaporator to completely vaporize, lowering the superheat. If the refrigerant does not absorb enough heat in the suction line to vaporize, liquid refrigerant will enter the compressor, causing compressor damage. A slightly overcharged system may improve evaporator performance. A grossly overcharged system will decrease evaporator performance. Low superheat due to metering device overfeeding. An overfeeding metering device will cause a flooded coil similar to an overcharge. If the sensing bulb of a thermostatic expansion valve is not insulated or properly secured to the suction line, the valve will overfeed. An incorrect or missing metering piston will also overfeed. Overfeeding increases system pressures. Low superheat due to low evaporator airflow. Low air volume reduces the heat load on the coil, so all of the liquid refrigerant will not boil off. Some liquid refrigerant could enter the suction line and possibly slug the compressor. Both suction and discharge pressures will be lower than normal. Dirty filters, dirty blower wheels and coils, bad motors, closed registers, and improperly sized duct systems can all reduce evaporator airflow. Low superheat due to low condenser airflow. Low condenser airflow increases condensing temperature, which also increases its pressure. This delivers refrigerant to the metering device at a higher pressure. The increased pressure drop across the metering device allows more refrigerant to flow through it. If the condenser loses its subcooling, then the evaporator will be starved, increasing superheat. The result is low or high superheat, high suction pressure, high discharge pressure, and low subcooling. The most common cause of low condenser airflow is a dirty coil. But this condition could also be caused by bad motor bearings, defective capacitor, shrubs, or other obstructions around the unit. Low subcooling. There must be enough subcooling leaving the condenser to ensure that no flash gas is being delivered to the metering device as it passes through devices and piping, which could cause pressure drop. Some possible causes of low subcooling leaving the condenser are loose TXV sensing bulb, inefficient compressor, low condenser airflow, low refrigerant charge, undersized condenser. High subcooling. If you have high subcooling leaving the condenser, here are some possible causes. Low evaporator airflow, high condenser airflow, high vertical separation with the condenser above the evaporator, incorrect or faulty metering device, liquid line restriction or faulty TXV, liquid lines exposed to low ambient temperatures, low outdoor ambient temperatures, oversized condenser, or a refrigerant overcharge. Typical subcooling example with a system containing R410A refrigerant. Liquid line pressure, 448 psi. Convert the liquid line pressure to temperature using a pressure-temperature chart. That would be 125 degrees Fahrenheit. Read the liquid line temperature using a temperature clamp. That temperature reads 105 degrees Fahrenheit. We subtract the liquid line temperature from the converted PT chart temperature of 125 degrees, which would give us 20 degrees of subcooling. Here is an example of a 410A pressure-temperature chart. Thank you for joining us for Essential HVAC Principles, HVAC System Diagnostic Fundamentals. If you have any questions or need more information, please contact the Cafferty Group Technical Service Advisors at one of our 12 locations.